Chapter 11, Areas of Polygons. Today we're going to cover section 11.7, Ratios into Areas. Our objectives for today will be to find the ratio and the areas of two triangles, and to understand and apply the relationship between scale factors, perimeters, and areas of similar figures. Comparing the areas of triangles. If two triangles have equal heights, then the ratio of their areas equals the ratio of their bases. Looking at the triangle here, there's two triangles. The height's not even shown in here, but if I do draw in the height, I can see that the triangle on the left and the triangle right share the same height. And if I even think about finding the actual area of each of the triangle, let's say I may put some numbers in here and told you that the triangle on the left has a base of 4 and that the triangle on the right has a base of 10. And we'll even make up that the height is 6. Okay. If I did find the area of the triangle on the left, the area would be 1/2 base times height, which half of 4 is 2, 2 times 6 is 12. The area of the triangle on the right would be 1/2 base times height, so 1/2 times 10 times 6. Half of 10 is 5, 5 times 6 is 30. And if I look at the ratio of their areas, it would be 12 to 30. And 12 to 30 I can reduce by 6 and get 2 to 5. And if I come over here and look at the actual ratio of the bases, well, the base would be 4 to 10, which would reduce to 2 to 5 as well. So the ratio of the areas is going to be the same as the ratio of the bases. And the big reason is, if I look at the formulas, the only thing changing in the formulas is the base. They both have the same 1/2 and they both have the same height. So ratio of the bases will be the same as the ratio of the areas. If two triangles have equal bases, then the ratio of their areas equals the ratio of the heights. So this is the same type of problem, except for the heights are different and the base is the same. So if I look at, here's the height of one triangle and here's the height of a second triangle. Since they both share the same base, when I go into the formula 1/2 base times height, the only thing changing is the heights, so the area will be in the same ratio as the heights. If two triangles are similar, then the ratio of their areas equals the square of their scale factor. Let's make up a scale factor to actually compare and look at something. So let's say I told you the scale factor was 1 to 3, and I made up some sides in the small triangle and told you that this was 3 and 4. Well, if the scale factor was 1 to 3, everything in the triangle on the right is really 3 times larger. So the left side would have to be 9, and the bottom would have to be a 12. So what this is telling us is that the area equals the square of the scale factor. Well, let's see what the areas would be. The triangle on the left, the area would be 1/2 times the base of 4 times the height of 3. Half of 4 is 2, 2 times 3 is 6. If I do the same thing for the triangle on the right, it's 1/2 times the base of 12 times the height of 9. Half of 12 is 6. 6 times 9 is 54. And if I now look at the ratio of the areas, it would be a ratio of 6 to 54. And if I reduce by 6, I get 1 to 9. So over here, original scale factor 1 to 3, ratio of the areas is 1 to 9, which is the square of 1 squared is 1, 3 squared is 9. And the reason it actually ends up being squared is, if I look at the diagram itself, the height is 3 times bigger, the base is 3 times bigger, so 3 times 3 ends up being 9. So it ends up getting bigger by the square. Theorem 11.7. If the scale factor of two similar figures is a to b, then the ratio of the perimeters is a to b, and the ratio of the areas is a squared to b squared. The reason for this really happening, I'm just going to imagine drawing two squares. Let's say the sides on the little square are all a, and on the big square they're all b. Well, if I did the perimeters, I'd get 4a on the left and 4b on the right. And if I reduced between 4a and 4b, I would just get a to b. If I did the areas, though, the area of the square on the left is a squared, the area of the square on the right is b squared, so the areas end up getting squared. So perimeters, same as the scale factor, the areas end up getting squared. Classify each statement as true or false. If two quadrilaterals are similar, then their areas must be in the same ratio as the square of the ratio of their perimeters. And this is going to be a true statement. And the reason it's true is it really just follows directly from above, saying if you look at the ratio of the areas versus the ratio of the perimeters, whatever the ratio of the perimeter is, you're going to square it to get the ratio of the area. And I can also look up above and see that the ratio of the perimeter is exactly the same as the ratio of the figures itself. If the ratio of the areas of two equilateral triangles is 1 to 3, then the ratio of the perimeters is 1 to the square root of 3. First thing you need to know is that equilateral triangles are similar figures, so that I can apply the ratios. And I almost look at this one in reverse. If I start with the perimeters, I know if I square the ratio for the perimeters, I should end up getting the ratio for the areas. And 1 squared is 1, and the square root of 3 squared is 3, and it does end up giving me the same value, so this is a true statement. Number 3, if the ratio of the perimeters of two rectangles is 4 to 7, then the ratio of their areas must be 16 to 49. And I do the same thing. First off, this says just the ratio of the perimeters of two rectangles. Here's the important part. If it didn't say rectangles, but said similar rectangles, then I would say it's yes, because 4 squared is 16 and 7 squared is 49. But it doesn't tell me that the figures are similar. So since I don't know that they're similar, I'm going to have to say that this is false. Number 4, if the ratio of the areas of two squares is 3 to 2, then the ratio of their sides must be square root of 3 to the square root of 2. Now, I know all squares are similar figures, so I can apply the rules. So if I go from the area to the perimeter, I can simply square root them, and I do get square root of 3 and square root of 2, so this is a true statement. Or you could have done this problem in reverse and said, if you start with the perimeters and square each of these, and the square root of 3 squared is 3, and the square root of 2 squared is 2, you do get the same ratio as the area is 3 to 2. The table refers to similar figures. Complete the table. Well, the big thing here is I know that the scale factor and the ratio of the perimeters, these two are exactly the same. So if I see that the scale factor is 3 to 5, the ratio of the perimeters is 3 to 5. The ratio of the areas, the big thing there is when I come from perimeter to area, I need to square everything. So 3 to 5, I square them. 3 squared is 9, 5 squared is 25. So as I go over to the next one and I see that I have 7/4, I know the scale factor and the ratio for the perimeters, same, so this is going to be 7 to 4. And when I go from perimeter to area, I need to square it. 7 squared is 49, 4 squared is 16. Well, the next one, I'm going from the area to the perimeter. So I don't want to square, I need to go in the opposite order, and I need to square root. The square root of 25 is 5, the square root of 9 is 3, and I know the ratio for the perimeters and the scale factor are going to be exactly the same. And the last one, the scale factor is 3 to k, the perimeter is going to be the same thing, so it's going to be 3 to k, and now I just need to square these to get to the ratio of the areas. 3 squared is 9, k squared is k squared. The diameters of two circles are 10 centimeters and 9 centimeters. What's the ratio of their circumferences and of their areas? Well, I know that circles are similar figures, and I'm looking at their diameters are in a ratio of 10 to 9. So now I want to know what's the ratio of their circumferences and of their areas. Well, the circumferences is similar to doing the perimeter, which should be the same, 10 to 9. And when I get to the ratio of the areas, I just need to square things. So 10 squared is 100, and 9 squared is 81.